Okay, so we're going to investigate this Rolle's theorem. So the first part here, the question telling us is asking us to is to graph these 2 points in this graph. So I'm going to graph 2, 2. I'm going to graph 7, 2. Then it's asking us to draw as many possible graphs through these 2 points as possible. All right. Well, here's one. That's a possibility. We could go underneath. Another one. I could draw something like a sine graph. Somebody in class also suggested just drawing a horizontal line through it. In each of those cases, there's at least one point where there's a derivative of 0. So the slope is 0, right? In this horizontal line, the slope is always 0. So that's what Rolle's theorem tells us. It says it's on a closed interval. If there's 2 points, 2 y values where the function is the same, there's going to be at least one place in between where the slope is equal to 0. Okay, and that's what we're going to do with this. See, the slope equals 0, the derivative is equal to 0. So let's scroll down here and do this next little bit. So they want us to show that Rolle's theorem holds here. So let's see. I know this graph factors to negative x minus 3, x minus 2. So it has zeros of 3 and 2. So let's graph that. So it crosses through 2, it crosses through 3. I also know that the x-intercept, or the y-intercept, will be 0 squared minus 5 times 0 plus 6. So that tells me it crosses the y-axis at 6. I could also find the vertex using that negative b over 2a trick you learned back in Algebra 2. So 5 over 2 times 1, well, that's 5 halves, or 2 1/2. So and that makes sense that the vertex is going to happen there. So let's see. So what is 5 over 2? Well, I'm going to get that function factored. Why don't I just use that factored form? Might be a little easier. So let's see, that's 6 over 2, so 5 over 2 minus 6 over 2 is negative 1/2, and 5 over 2 minus 4 over 2 is positive 1/2. That tells me the vertex is at 2 1/2, 1/4, negative 1/4. So we're right about there. So this graph looks something like this. Okay. So, is the curve continuous? It sure is. Is it differentiable? Yeah, it's a polynomial, no corners or cusps or holes. And that's why. There's no corners, cusp, holes, vertical tangents. It's a nice, smooth, well-behaved curve. So now we're going to use Rolle's theorem to find out that x value, which we already know the answer is that x is 5 over 2. So let's use calculus and Rolle's theorem to show this. So this Rolle's theorem says there's got to be one place between those 2 values of 2 and 3 where the derivative is equal to 0. So I'm going to take the derivative. I'm going to say f prime of x equals 2x minus 5. Then I'm going to say, where does that equal to 0? Where does 2x minus 5 equal to 0? And if we add 5 divided by 2, we get our 5 halves. So that's what Rolle's theorem tells us. Let's try another one. Okay? So this is find all values between the x-intercepts, which Rolle's theorem holds for the roots of that equation. Well, let's see. Where does this equation cross? Where does f of x, I'm going to factor out an x squared. Okay. That leaves me 3 minus x squared. So let's see. The 0 is going to be 0, and x squared equals 3, so x equals plus or minus root 3. So we've got three zeros. So I know that this graph crosses at 0, 0. I know it crosses at negative square roots of 3. I know it crosses at positive square roots of 3. Yeah, I also know that since this is a a 4th degree equation, it's like a parabola. So it must be it looks something like this. Okay, so it's got to cross those 4 places. It's negative, so it's got to open down. So we see there's going to be 3 places where the slope's going to be 0. So now to use Rolle's theorem, let's take the derivative. And factor out it. We want to see where that equals 0. And we're going to ask ourselves, where is that equal to 0? Well, it's equal to 0 when x equals 0. It also is equal to 0 when this mess equals 0. And that's going to be plus or minus the square root of 3 over 2. I mean, we could rationalize that. But we've answered the question. Those are the 3 x values where it's equal to 0. And if we graph this on a calculator, I would highlight, we know that that's going to be the square root of 1.5, negative square root of 1.5. That's positive square root 3.5. That's 3.5, 1.5. Okay, and that's where the slope is 0. Okay, so that's Rolle's theorem. So now this second part, it's asking us, the mean value theorem is just it's almost like a continuation or collar area, they call it, of Rolle's theorem. Or maybe Rolle's theorem is a corollary of this. But what it says is if we have this tangent line right here, that tangent line right there, that tangent line right there, there's going to be one point on this curve right there where that tangent line is going to be parallel to that secant line. And all the mean value theorem says is, in fact, you might want to, let's see, you might want on paper write that's f prime of c. So basically what this says is the slope of the tangent line is the same as the slope of the secant line. Okay, so let's apply this to this problem. So we've got the point, well, they want to find the secant line on the interval 1, 5. Well, we could do this graphically. When x equals 1, y equals negative 2. So 1, negative 2. And when x equals 5, y equals 2. And we could check plugging those in the calculator, or plugging those in the formula. We don't have to. So this is asking me to actually draw this beast. So let's do that. This line. Okay, so there's the secant line. And I'm looking for some point on this curve. What do you think? Right about there? Where that tangent line is parallel to that secant line. And this x value here is the c that they have here in the equation, right? See how they have the c? Well, that number there is the c. And we're looking for the point where that tangent line is parallel to the secant line. So the mean value theorem says, well, find the slope of the secant line. Well, we've got a x2, y2. We've got a x1, y1. Or f of b minus f of a, depending on how you want to think about that. So the slope on the right-hand side is going to be 2 minus 2, y2 minus y1, over 5 minus 1. Well, that's going to be 4 over 4, and the slope's 1. Now, for the right-hand side, they're telling me take the derivative. So I got to take the derivative of this function. Well, the derivative of 3 is 0. So f prime of x3, the derivative of 3 is 0. And then we're going to think of this as negative 5 times x to the negative 1. Bring the negative down, take away 1. So that's going to give me 5 over x squared, right? Now, to use the mean value theorem, get this out of the way. we're going to say, where does this slope on the left, and I use c because they have c in the formula, I could leave it x, equals the slope on the right. And if we solve this equation, we're going to just think of it like a proportion. I know that c squared equals 5. C equals plus or minus the square root of 5. We're going to discard the negative root 5 because we're on the positive axis. So this c number is going to be positive root 5. And we could substitute that in and probably find the y value, but they aren't asking us to do that. They just want us to find what values of c make this tangent line parallel to the secant line. So positive root 5 and c equals positive root 5. That's the solution. Okay, let's try the next problem. Okay. So find the equation line tangent to the curve at the point at which the solution was. So that basically what they want us to do is find the slope of that secant line, right? Find the slope of the secant line just like what we did, and then find the equation of that line. So we know we're gonna use the mean value theorem, right? So which tells me the slope of the secant line, is the same as the derivative at that point. So I guess let's do this. Let's find what f of pi is. That's going to be my f of b. So 2 times pi plus sine of pi plus 1. Well, sine of pi is 0. That's going to be 2 pi plus 1. Okay, and then what's f of 0? Well, 2 times 0 is 0, plus the sine of 0 is 0, plus 1. Okay, so that's our f of b minus f of a. So f of b is going to be 2 pi plus 1 minus f of a, which is 1, all over b minus a. Well, that's going to give me, let's see, the 1's cancel, the pi's cancel. The slope of the secant line is 2. Now let's take the derivative. Let's find f prime of x. So the derivative of 2x is 2. The derivative of sine is positive cosine. And the derivative of 1 is 0. So then we're going to set these two sides equal. I'll replace the x with the c to keep the mean value theorem happy. So what's fun? 2x plus the cosine of c has to equal 2. The derivative at that point is equal to the slope of the secant line. That's what I've done. So I'm going to solve this equation. Cosine c equals 0. So then I've got to ask myself on the range 0 to pi, when is the cosine equal to 0? Well, I think it's at pi over 2, right? So c equals pi over 2. Okay, now if we want to graph that on a calculator, okay, got ahead of myself. I don't want to graph it on the calculator yet. I got to find the equation of the tangent line. So what we're going to do is, I know the slope of that. I know where the slope's parallel. I know the slope is 2, and there's my x. Now I just got to find the y for that point, the point on the curve where that's the slope is parallel. So I know x is pi over 2. So what's f of pi over 2? F of pi over 2 is 2 times pi over 2 plus the sine of pi over 2 plus 1. Well, that's pi. That is 1. And that's 1. So I'm getting 1 plus, or pi plus 2. So I've got the point pi over 2, pi plus 2, and I've got a slope of 2. So now my equation of my line will be this. And I'm going to put this in a form that I can put in my calculator. Well, maybe we'll just clean it up. I'm going to do 2x minus pi. And then I'm going to add pi over 2 to both sides, or add pi plus 2 over both sides, plus pi plus 2. So the pi's cancel out very nicely. So that tells me that my tangent line is going to be 2x plus 2. Let's graph that and check. Oops, not negative 11. I only want negative 1. Just to put it either side of it. I don't know. Let's try negative 10, positive 10, and see what that looks like. So there's the original line, and there's the tangent line. And let's hit trace. Let's do pi over 2. And there, that looks pretty good to me. I think we've got it. Okay. I'll stop this here.